Okay, so we're in section 6.2. We're now talking about volumes. So section 6.1, we were talking about finding areas between curves. In 6.2, we're going to use calculus to help us find volumes. And a number of you have told me that there are solids that you already can find volumes for because there are formulas, like, for instance, spheres and cylinders and cones and rectangular prisms and so forth. But we can actually find volumes for a variety of other solids that would incorporate the formulas for those solids as well, using calculus. So let me show you how this works. Okay. So again, here are some of the standard solids you already know how to find volumes for, and there are the formulas. Um, and what if, hold on, I don't want to go to exercises. Hold on. Let me keep going down here. Okay, look at, you see here in figure 2. Figure 2, you have a solid. It looks like a loaf of bread, doesn't it? It's a solid. And the solid is parallel with the x-axis, and it goes from x equals a to x equals b. And if we were to cut out a cross section of this solid, that purple cross section there, the cross section would have an area, right? And the area would be a function of x, because depending on where you cut out a cross section of the bread, the areas can change, and that's because x is changing. So the cross-sectional area is a function of x, a of x. Now, what if we wanted to find the volume of the well, if we were to divide this solid S into into slabs, okay, or slices, then what we would have is what you see here in figure 3. So you have there in figure 3, the first picture, you have a slab, okay, or a slice of this volume with width delta x and cross-sectional area a of x. Okay, so we can find the volume of that ith slice or slab by taking the cross-sectional area and multiplying it by the delta x, the width, because area times width is equal to volume, right? So think of, like, areas in square feet, width is in feet. If you take square feet and multiply it by feet, you get cubic feet. That's volume, for instance. So in figure 3, the second picture, now they're breaking that solid up into lots of slices. And of course, the more slices we have, it's definitely a 3D picture, sure. The more slices we have, the better the volume approximation is going to be. So they talk about, they call the slab a cylinder. The volume, let me just go down a little bit here. So the volume of the cylinder or the slab is a sub a of x times delta x. Okay, that's the volume of the ith slab. And if we wanted to approximate the volume of the full solid, we would add up all the volumes of the slabs. Okay, and that would be your approximation. Now, naturally, as you take more and more slabs, you're going to be able to approximate the volume better and better. And so if we let n, which is the number of slabs, go to infinity, this volume is going to approach an integral. So it's a Riemann sum will approach the integral. And this gives us the definition then of volume. Okay, so if you have a solid between x equals a and x equals b, and the cross-sectional area of S, well, let's not get if you have a solid between x equals and x equals b, and a of x is the a of x is the cross-sectional area of each slab, then the volume is equal to the integral from a to b of a of x dx. Okay, so that's now we have a formula for finding a volume. Okay, are there any questions on that? All right, well, let's look at an example here. Let's look at an example. So in example 2, they talk about using the disk method. Now, what's the disk method? Okay, so find the volume of the solid obtained by rotating about the x-axis the region under the curve y equals square root of x from 0 to 1. Illustrate the definition of volume by sketching a typical approximating cylinder. So, all right, well, let's look at the picture here. Figure 6. This is what we're doing. So you see the first picture, we have a region bounded by the x-axis and the vertical axis, the vertical line x equals 1, and then y equals square root of x. We're going to take that region and we're going to rotate it around the x-axis, and that's going to give us the solid you see below in figure 6. And we want to find the volume of that solid. Now, that's not a solid that you have a formula for, right? You don't have a, that's not like a sphere or a cone or anything like that. It's a new solid. But yet, using calculus, we can find the volume of that solid. So they have their picture where they're putting in a cylinder, a disc, and delta x is the width of the disc. So just like with areas in section 6.1, yeah, just like in section 6.1, in the pictures, you know, they have vertical rectangles with delta x width, and then horizontal rectangles with delta y width. We can do the same thing with volumes. We can have vertical discs with delta x width and horizontal discs with delta y width. So the cross-sectional area of that cylinder in figure 6, we know the width is delta x. The area of the top of the cylinder would be the area of a circle, right? So what's the formula for the area of a circle? What's the formula for the area of a circle of radius r? That's right, Tosh, pi times r squared. Okay, so the area of a circle is pi times r squared, where r is the radius. Well, in figure 6, what would the radius be for that pink or purple disc there? What would the radius be equal to?
Square root of x.
I'm sorry?
Square root of x.
That's right, Ange. Very good. Square root of x. And square root of x, the radius is going to change based on where x is. So square root of x is the radius. So the area, the cross-sectional area for that disk would be a times the square root of x squared. And so given that, then, using the formula we just learned this formula for volume, right? If we want the volume for this example 2, the cross-sectional area is pi times the square root of x quantity squared, which is pi times x. So then here is how you would find the volume of that bowl-shaped solid in figure 6. Please let me know if you have any questions on that. That's right, Sandia. The square root of x is the radius. That's correct. So, I mean, look at this. Now you're able to find the volume of an interesting solid, and the volume is equal to pi over 2. That's the exact volume. And you want the exact volume. If that bowl is going to hold, say, like juice or something, or soup or something, you want to know the exact volume, because that affects, like for business, that would affect their bottom line, right? They need to know that in order to determine profit and so forth. So this is an introductory example to section 6.1. And it's absolutely amazing, I think. It's absolutely amazing that we know the volume of that bowl there in figure 6, that the volume of that bowl is equal to pi divided by 2, whether it's cubic inches, cubic feet, whatever. Are there any questions on this? All right, well then on that note, let me stop the recording.